Hi guys. We're doing the assembly talk today, so thank you for coming, although it's like really cold today. I'm Hayun,
I'm Evan.
and I'm Asrita. So welcome to our talk. For show of hands, has any of you taken 230 or 198C? Okay, good to know. So, you might, if you've taken any of those classes, you might know assembly before, but a quick rehash is that assembly is a low-level programming language that lets your computer interact directly with its instructions, which is important, and we're going to go more in depth about like some of the benefits of assembly. But first, I'm going to be talking about the von Neumann architecture. So von Neumann was this old guy that creates a wonderful thing. Basically, this architecture, if you have a modern day computer, which I'm sure all of you do, as I see, it's all based on this one architecture. This is important because it allows us to use the memory space to store both instructions and data. So there's 5 parts of this architecture, as you can see for this diagram. Okay, so you might have seen this before if you took into the 198C, but we have our control unit, our memory unit, input devices, output devices, and system bus. But let me first explain about our CPU, which you may have heard before from different sources. So we have our control unit, which takes down our instructions, or which you can think of as like kind of like tasks. So think of instructions as sort of like your to-do list, where you're like kind of like checking off each single one. So what the control unit does is it takes our instructions and kind of understands it, and our ALU, or our arithmetic logic unit, basically understands, like basically does the task, so it performs like mathematical operations. And I'll be talking more about registers like moving on. But going to our memory unit, which as the name implies memory, it allows us to store both data and instructions, and it's where the RAM lives. And now moving on to our input devices and output devices. As the name implies, we take in our inputs, so our data, so like our mouse and keyboard, and our output can be anything from our computer screen, which will show us the result of this entire process, the control unit, as well as maybe like a printer. And now onto the system bus. So this is actually quite complicated, but a high level understanding of this is, you can think of it as the highway of all this information. You can see that it's connected to every single part that I just showed you. So it sort of serves as like, I guess, like transportation or bus, as the name implies, for all these different parts. And now I'm going to be talking about the fetch decode cycle. So fetch, as the name implies, is where the control unit that I mentioned in the previous slide will retrieve like the next instruction or like the next task that we have. And our program counter holds like our holds the next, will point to our next task that we have to do. And our instruction or task is loaded into our instruction register, which is like what's pointing to our current task that we have to do. Okay, I'm just not gonna use the mic. It's like reverberating. Can you guys hear me all right? Okay. So our decode, which is our next step, is where our control unit interprets the instruction, kind of understands like what it's doing, and then determines like what operation that it needs to perform, maybe like division or addition. And then it'll identify the required operands and your locations, like the functions it has to go to, or like in terms of like yourself, like where you need to go to perform this task. And finally, execute, as the name implies, will actually execute our task. So the ALU, or the arithmetic logic unit, will perform this operation, and it'll store this in registers or memory. You'll see more of this, don't worry. And our program counter, so which is keeping track of like the next task that we have to do, will update to our next task. And this will all happen again. It'll keep repeating until we're done with it, with all our tasks or the end of the day. Before I move on, does anyone have any questions or about any of the parts that I just explained? Okay, so now let's explain the compilation process. So if you guys ever coded in C or Go, you may have seen this command, is for C. So when we first write our high-level programming code that we can understand, our computer won't actually understand it, so we need to go through this translation or compilation process. We can ignore part of the preprocessor. It's still not legible by our program, but okay, let me move the slides. So onto our compiler. So what our compiler will do is it'll take in our code and make, although it's still human readable after our compiler, what it does is it essentially translates it into assembly, which we'll be writing. So be excited for that. And then it'll optimize things so it won't be completely like one-to-one, so it won't be like our code into the instruction, but it'll make it into assembly code. And then we move on to the assembler, our second step. So what the assembler does is it maps these symbolic instructions and opcodes, and it produces machine code to the hardware components. So it'll create a .o file or an object file, but it's like non-executable, so you can't really do anything with it. The next step is the linker and loader, which we won't be explaining because it's like really technical and a little bit confusing. Basically makes this .o file into the executable, so it actually runs your code and makes the computer understand it. Sorry. Now Evan will be explaining the machine code and more about assembly.
Awesome. So when you create assembly code, we were all looking at when we create assembly code, when you were looking at that, it has all these nice human readable things for us to look at. We had things like move and add and subtract and multiply, all these different instructions that give us a hint as to what the code's doing. And although that's great for us, for a computer, all those words and strings don't really work out well. So when you're actually running your assembly code on a computer, it is first assembled into machine code, which is basically just like a byte representation of what you're doing. So example, when we have move, add, and subtract, and things like pop and return, all of those values are assigned to a byte. And that's how the computer identifies what instruction we're trying to run at any particular time. And then all of the registers and all of the offsets we're using are then used in subsequent bytes. And so when we use a byte to represent the instruction we're doing, the computer automatically knows, okay, hey, here's how many bytes I should expect after that. And then that's how it knows how to run the code. And so just for a quick demonstration, if everyone's following along, go to the website godbolt.org, and just once you get there, start looking at the difference between the left and the right panes on the website. So what Godbolt does is it's a automatic compiler. So what it will do is whatever code you write on the left, so in this case this is C++, we have our function square, whatever code you write there, it then compiles and shows you the actual compiled code on the right. So you can do a little compare and contrast or a little reverse engineering work of your own to decide, oh, I wrote this function, here's how it actually looks in assembly. And if you're in 367, this is one of the main ways the professor talks about getting better. You write some piece of code, whether that be like a binary search, or you write an object, and then you see how that's actually represented in assembly. So everyone just takes something like, I don't know, 5 minutes, 10 minutes, write something in C++, see how that's assembled, and then after that we'll explain this example, and hopefully if anyone wants to share their example, we can present that up here and kind of do a little reverse engineering for that. So we're just going to give everyone 5 minutes to play around with that. That's good.
Sorry everyone for the lighting difficulties. We are not that familiar with how great the slideshows are, so.
But if anybody wants any help, feel free to.
Oh yeah, if anyone wants any help, we'll be here to help you. Are you having any trouble with Godbolt?
No, I just wanted to see.
Oh, I think if you don't know C, there should be an option where you can check out a bunch of different languages.
Oh, I see. All right, thank you. Does anybody have
not see the whiteboard, Leon?
No, I can't.
All right.
Oh, I can see it.
Go ahead.
We can
Draw big.
draw big. That's good. I don't think it's an eraser. Awesome. Is everyone all set with Godbolt, or do you guys want a little more time to play around with it? Whoa.
I'm sorry, I'm gonna turn it down.
Yeah, I think
That's-
it's
that's
good.
good. So,
Yeah.
yeah. So if we look at if you look at your Godbolt code, you haven't learned the instructions yet, so it might be hard to figure out what it's doing. But we can go over this example right here, where in C, we're taking the number and we're just returning the value of that number squared. So what are we actually doing in the compiled code? Well, for the first step, we'll get into this later, we'll just ignore these first two steps. That's something the computer does to keep track of where we are, so we can just ignore this. And then what it does is it takes some number from EDI, and then it moves it into the location of RBP minus 4. And so RBP minus 4 is just an offset, just a location on the stack where we can move stuff. And EDI is the register where the arguments we pass into go. So we have this variable num. So num is at EDI, and then we take EDI, which is num, and we put it into RBP minus 4, that location on the stack. And then we move our location onto the stack into this register EAX. Then we multiply EAX, and then return our function. When you have a function and you call something, all the return variables are just stored. When you return something, it's just stored in EAX. So that's why once we multiply it and store it in EAX, we don't have to do anything different to that. And then, so we talked a little bit about storing variables. And there's this weird concept called endiness. And what endiness is when we're reading numbers, say we say something like 401. When we represent this, we go 400, nothing in the tens place, and then 1. And basically, what we're doing is we're saying the most significant bit first, which is the 400. And then we go down as the numbers become less significant. And what a lot of computers do, weirdly, is they actually store all the numbers in a little ending format, which means that the least significant byte is stored first. So example, if we have the decimal number, and of course we're not working in bytes, but if we have the decimal number 367, if we knew this number was stored in the little endian, what would this number actually be? Does anyone volunteer and give a suggestion? Perfect, yeah, it would just be 763. It's just the least significant bit first. So the least significant bit is the second most significant up until the end of the number. So when we're actually working with computers, what we'll see more likely is we'll see bytes. So what we can do is we'll represent this in hexadecimal, which is just a base 16 format. We have 872931. And what we actually do is when we store it in hexadecimal, we store it per byte. So each pair of 2 is a byte. So when we actually reverse this, although we switch it around like we did in that previous 367 example, we keep the bytes together. So 8 and 7 stay together as they are, 2 and 9 stay together as they are, and then 3 and 1 stay together as they are, but their order switches. Does anyone want to give another suggestion on how this would be represented in a little endian? All right, so this one's a little bit harder just because that whole byte thing. But what we do is if we store this in little endian, we know this is the least significant, this is the second least significant. Oh.
Why is 87 the least significant again?
Oh, so 87 would be the least significant because if this is being stored in little endian, that's how we store the bytes. We store it as the least significant to the most significant. If you remember that 367 example, we have the number 367. The 3 is the most significant because it's like the 100, and the 7 is the least significant. So if we were storing this number in little endian, so if we were storing this number in little endian, the least significant bit would be stored first, which is like the ones place. So it would be the least significant bit, the second most least significant, and then the third least significant. So the most significant bit, so that hundredth place is stored like last. Does that make a little bit more sense? Or is that still confusing?
I kind of get it.
Yeah. It is a very confusing concept. Like the first time I heard of this, I was like, ugh, I got no clue what I'm doing. But let me just erase that. But it's basically just like if something is stored in little endian and you want to get it to big endian, a number we understand, you just have to flip it. So what we would do here is we would do, since we talked about it earlier, all the bytes stay together, all the pairs of 2. This number would be 31, 29, 87 if we store this in, if this was stored in little endian, this is what it would be in big endian. And we're talking a lot about storing numbers. So one thing is, how do we actually like store these numbers? Like we haven't talked about memory, we haven't talked about storage at all. And this, this is where that comes into play. So we have this idea called registers. And registers are, if you have your CPU, registers are built in right next to the CPU. So when you're like adding numbers and multiplying numbers and subtracting stuff, when the registers are so close to the CPU that it makes all those calculations so much faster, which is why we store everything in registers. And there are 6 general purpose registers. So those can store any value, any 4-byte value can be put into any of those general purpose registers. And then there are 3 reserve registers, which are EVP, ESP, and EIP. We'll get into all those later. But basically, you can think of any of the general purpose registers like a bucket. You can just put a value in that bucket and then take it out when you need it later. And those are right next to the CPU, so those are all very, very fast.
And each one's a bucket. Are there like multiple buckets of the same type, or are there just those?
Think of them like 6 different buckets, and you know which one you want to take a value from because they're all labeled differently. So there's EAX, EBX, ECX, and and all the other ones. And you know, oh, I want EAX, so you reach in the EAX bucket and take a value. Or you could like store a different value in there.
How do you store more than the 624 values?
That's a good question. So we'll get into that in the next one. So as you notice, there's 6 general purpose registers. How many people here have created a program that needs more than 6 variables? Everyone here shouldn't be raised. You should have complex programs. So exactly. So if you have 6 variables and you need to store them all at the same time, the register format really doesn't work. Even though they're very fast to compute and we would theoretically want everything in a register, they're just so expensive to put on the CPU that we can't have a lot. So what we do to fix this is we have a thing called the stack. This is how memory is actually stored. And what the stack does is it's a first in, first out data structure. So what that means is whatever we put on the stack is the first thing we take off the stack. And we can and we do this with push and pop. We'll get into that in the next slide. So when we push, every stack address is given the stack is given a memory address for every kind of variable it has. So it starts from a high memory address and then it goes to a lower memory address. So the stack goes downward. So when we push something onto the stack, we basically push it onto the bottom of the stack. So when we're pushing, say this is our stack and we want to store a variable. We don't need it in a register. What we would do is we would just push it to the bottom of the stack, and then if we remember its memory address, we can access it later whenever we want on this stack. And say, we have that variable, we use it, we don't need it anymore. If we just keep pushing stuff to the stack, we're going to have too much data. We're going to have too much data stored. Our computer's going to run slow. So what we need to do too is pop. And that's where whatever we just put on the stack, if we pop it, it takes whatever's at the bottom of the stack and it gets rid of that. And that's a way we can make our programs more efficient, we can save data. And one of the biggest things about popping and pushing is actually functions. So how a function is run in memory is when we call main, basically when we call main, we put all of the local variables of main onto a stack. So example, so we have all the variables relating to function 1, all the variables relating to the return, and the RMC and RMP. All those are on the stack. But when we call function 1, we don't want to put all the function 1 variables in the same section of the stack. So what we actually do is we create a whole other thing called a stack frame. It's basically just an extension of the stack, and we start adding all the local variables for function 1 onto this section of the stack. And then we have function 2 is called, so then we add all the variables for function 2 down there. And so what we do is, say we, how the instructions work, or now that we have all those frames, if we have function 2, and function 2 finishes, we don't need all those local variables saved anymore, we can just pop all the variables relating to function 2 up the stack. Say function 1 finishes, we can pop all the variables relating to function 1 off the stack too, and then all we'd be left with is that main. So basically when we do this, it's just a neat way to clear variables up when our function finishes. All right. And if all of you remember, there were those 3 special purpose registers. I was like, hey, don't worry about these. And so these are coming back into play. So when we have this stack and it's growing and shrinking and growing and shrinking constantly, how do we actually keep track of all of the data on our stack? And that's what we have those special purpose registers for. So what EBP does is EBP points to the top of the, EBP points to the bottom of the current stack frame, and ESP points to the top of the current stack frame. Again, because the stack's growing down, it might be weird, because the stack growing down, this is the top of the stack. So in your mind, you might be able to flip that over and that might help. And so what we can do is if we know, we'll always know the value of ESP because it's always going to be stored in our ESP register. We'll always know where EBP points to because it'll be in our EBP register. So if we keep popping variables onto the stack, what we can do is this is a lower address, this is a higher address. We know that whatever value in here, whatever value is in here, we can get with ESP. And whatever value, if all these are 4-byte values, whatever value is in here, we can get with ESP plus 4, if we get that address. And then ESP plus 8, and then ESP plus 12. And so basically, ESP and EBP are 2 ways where we can basically remember where all our variables are stored on the stack so we can access them later, because we can't store everything in a register. And this also comes into play with actually how functions get called, which is really cool. Go.
Hello. Oh, I don't know if it's on. Okay, whatever. Okay, so we're gonna go over what happens when a function gets called on the stack. So I already talked about the function stack frames. All of the local variables within a function will be contained within that function stack.
Okay, never mind, we're not using this.
So in this code here, main is going to call the sum function. That should be sum this time. Okay, so main is going to call the sum function, and the sum function takes 2 arguments, num1 and num2, and it's initializing the local variables x and y, and then it's passing in the values of x and y into the sum function. So on the stack, how does that look? First, we have our EBP and ESP, like Evan talked about, and when you push stuff onto the stack, ESP is going to go down, right? Because the stack grows downwards, so every time you push something onto the stack, ESP is going to decrease in what address it's pointing to. So when you call a function, in this calling convention that we're using, function arguments are going to be pushed in reverse order. So the add function takes in num1 and num2, so we're going to push y first, and then we're going to push x. So on the stack, you can see it has 4, like the value of 4, which is x. So does everyone get that? It's like it's kind of pushing the arguments that it's going to call for the add function, or sum function. Okay. So next, what happens is it actually calls the sum function, and when a function is called, the compiler or the computer does 2 things. It pushes the return address, which is the address of the next instruction that it's going to execute, which would be the address of this return 0 instruction here. So it can know to jump back to that instruction when this function finishes executing. And then we're going to talk about how that works too later down in the presentation. So don't worry if this part doesn't make sense. But after that, we're going to create a new stack frame, right? So all the stuff in orange is the stack frame that corresponds to the sum function. And when you create a new stack frame, you have to reset the EBP and the ESP values because they point to the top and bottom of the stack frame, not the entire stack. So we're going to reset those, and when it resets that, the computer is going to make space for all of the new local variables that are going to be in this sum function. So it decrements the stack pointer so there's like space to store all of this stuff. So we've set those up, and you'll notice that it pushed EBP up main onto the stack. And it pushes that because when we're done, executing stuff in the sum function, we have to know how to go back to the main function, right? So we have to store the old EBP so we can go back to it somewhere on the stack. And so we're just gonna push it onto the stack and then go into the next function stack, right? And then, so now we have to access that 4 value. So you might be thinking we already have the value 4 on the stack. Why can't we just move it from this address to that address? So we can save space, right? Instead of just putting it twice. But you can't do that on a stack. You can't just move values wherever you want. You have to go through registers. So in this example, you could put it in EAX, you put the value 4 in EAX, and then copy it back onto the stack. So you have it twice. And then when you look at the assembly for some code that you write, for example this code, you'll see that it does some instructions where it moves it into an intermediate register and then pushes it back on the stack. So that's a pattern that you can look out for when you're looking at assembly. Yeah, so sum is another local variable that within the add function, so it pushed the value of 6 onto the stack. So Hayun's going to explain x86 instructions.
So currently there's different types of assembly instructions for each one. But we have a manual for Intel x86. It's 600 pages, so it's a little bit intimidating. But you don't need to know all of these instructions. Basically, as you can see from the graph, it's really skewed towards a certain set of instructions. So if you know those, you're pretty much set. And now we're finally going to be talking about the instruction format. So you'll be learning how to write assembly. So yay! So as you can see, there's the operation argument. It's going to be the same for every single one. So it's going to be the destination, then it's going to be the source. And let's move on to the move instruction. So for move EAX 0x4, what that's going to do is it's going to take the value 0x4.
Sorry. What the heck?
Sorry, everyone. We don't know how to use this equipment.
Just don't do anything with the equipment. We can just present without the mic.
What was that?
Okay, anyways, so what this will be doing is it's going to put the value of 0x4 into the EAX, as you can see on the screen. And then if we, for this one, this is really important. You'll think that because it says EBP minus 0x8, it's going to take the value of EBP, so the value over there, and put it in EAX, but that actually isn't true. What this is doing instead is it's going to point to the memory address that EBP minus 0x8 is. One way of thinking of this is, this might be a bit confusing, but when it says EBP minus 0x8 and there's no brackets around it, you can think of it as just, it's getting the name of it, so that's be the address. I'll show you what I mean in a sec. With the brackets, we're actually getting the value that's stored at that location, so at that address location. It's dereferencing, but an easy way to think about it is, if it's brackets, it's a box, we're actually going inside the box and taking out the contents, but if it's just the name, we're just grabbing the box and not actually going inside the contents. If you're confused at any time, raise your hand. I know the dereferencing part might be a bit confusing at first, but let's go to add EAX, EBX. So you can see the values of 0, 3, 0, 0, 0 for EAX, and for EBX you can see 0, 5, 0, 0, 0, 0, and this is the add command. Does anyone want to give it a go? Okay, I will. So what we do is we take this value, and what we take the value inside EBX, and then we add it to our 0, 3, making it 0, 8. So that's just the add function. Easy to remember, it's just add. And then if we go to add EAX 0, 4, that's the same thing. It takes our empty EAX value at the moment and changes it to 0, 4. It's that simple. Yes.
What if the addition goes to 3 digits?
What do you mean by that? Could you clarify?
80 plus 30.
Wait, so these are all remember when Evan talked about So these, like, this is all how the computer represents it. So this is all little endian format. So if you had, then these are 32-bit registers. So if you had like 80, for example, this is also hexadecimal notation. So that can still be represented like in hexadecimal notation, right? So take whatever the hex value of 80 is, and then let's say like it's like 4 bytes long, or let's say it's like multiple bytes. You would just like store it in here, like, and then if you add two things, wait, can you go to the next slide? Yeah, it's like if you add two things, you can just like store it like in these parts. Because this is 4 bytes wide. Each of this can represent up to like 256 in decimal. So like you can get like a lot of representation with like 4 bytes. It's like up to like 2 million or something. I don't know, but like you can represent very big numbers in this. Does that make sense? Okay, like what are you confused about?
So like, what would 80 look like? Would it be 0, 0,
What's 80 in hex?
or just a big number?
5.
That's 5. No, 5 3. 5 3.
3? Okay.
No, 16 times 5. Wait, oh my god.
What is it?
Oh, is it 5?
It is, yeah, it's 5.
Okay. So this is decimal notation. Computers use hexadecimal notation. So it would be, what is it, 5? Okay. So that's how 80 would look. So it's still 5, oh. So yeah. So it would still fit in like, one chunk of that register. Because if you have the register, you have 32 bits total, and this is each one byte, which stores into 8 bits. So you can store up to, this is all hexadecimal notation. So this is the max value, which translates to like, this is like the maximum value that you can store. Like, let's take a really big number, right? Like, let's take like 1,000. So what would that be? We don't have the computers.
Okay, wait, I can just do okay. So I think I'll first like explain what bits are because you guys might be confused. Okay, so we have this, right? Let's say so in bits, it would be 1, 2, 4, 8, 16. But what hex does is it makes this into that one thing, and so this itself, when we did FF, right? So this will refer to 1 here and 1 here, and that will be the value. So if I think I'm confusing you. Let me take a step back. But what I'm trying to say is, this would be decimal format where we would have these values. So this would be, let's say, 80, right? So 80 would be 5, 0, 0, 0, 0. So in hex, this gets corresponded to 5, 0. Yes, because this is ones and this is 16. So it's hex. Yeah.
How is 85, 0, 0, 0? I thought.
No, this isn't decimal.
It's just because in hexadecimal, like 10 is 16. So you have like, that's why you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Like, so that you have 16 digits that you can represent numbers with. So when you translate between decimal and hex, you have extra digits that you can access. So you have to do this like translation that you was doing. And then these mean 80, like to us, like they mean 80 as in like the value they hold is 80. But 50 is like another way of representing it. Like it's another notation. Like you have binary, which is just like ones and zeros, right? You only have 2 digits. And then you can represent 80 in binary too, and it's just like ones and zeros.
You might be, wait, I think a better example is I'm just going to take a number, let's take the number 80. So there's different things called bases. There's different bases, right? So decimal will be base 10. They could be base 3, base 2. But what you can think of them is you can think of them as different languages in math that represent the same things, the same word. So if we have base 3, for example, this will represent 1s, 3s, and 9s, right? So 9 times 8 is 72. So 72, and then we have 2 6s, so 78 and 2. So in base 3, it would be 822. But in base 10, which is what we've talking, it's 80. Does that kind of clarify things? Like base 16 is instead.
Oh.
Yeah.
I thought you were doing addition with the 16. I thought it was 16 plus 0 but it's 16 times 5. Alright, sorry.
Yes. Think of it as like this would be 9 times 8. This would be 3 times 2. It's 1 times 2. So in hex itself, this this is 1 and this is 16. So it'd be 16 times f, which you haven't gone over, but f is 15. So 16 times 15, and this would be 15. So you don't have to worry about this. You'll learn about this in your 230 classes. But what I'm trying to say is, even when we do like really big numbers, we can still represent them because it's in hex, and because as Shrija mentioned, one thing is 256. So if we have that for like a really big string of numbers, we can represent almost all of them. Does that kind of explain things?
Yes. Thank you. Sorry for the.
No. Feel free to always like ask questions. We don't want you to be confused. Okay.
Yeah, and then the maximum value that a 32-bit register can store is like, I looked it up, 2,147,000,000, blah, blah, blah. So like, you have like a lot of numbers, like you have a lot of space to like store big numbers. So, yeah.
Oh, it's 32 bits.
Okay, would anyone like to do the sub EX, EBX? This is subtraction, by the way. I'll give you guys a minute or two to kind of like talk to the person next to you, and then try this out, and then let me know.
So it's hex. 8,000 minus what? Hex better than this one. This has
Leon, it's a little envious.
Oh, yeah.
Oh, so 8 minus 5.
Yeah.
So 3.
Yeah.
Great job, Leon.
So 60 there was a transfer file. Yeah, sorry.
Okay, would anyone like to
Oh,
be brave
that's-
and volunteer?
But if I need CX.
Already do that. Okay, then I'll reveal the answer. It's 3. It's 8 minus 5. It's 3. Does everyone understand why it's 3? Yes. Yes. Good job. Okay, now we're going to be talking about the push instruction. Evan briefly explained this, but I'm going to explain it again. When we have push 0x4, we're pushing that value onto the stack. So our ESP, which is pointing to the bottom of our stack, so that one, since the stack goes downwards, as we mentioned before, our ESP moves down, and 0x4, a new box is created and pushed onto the stack. And the pop instruction is like, as you saw in the previous animation, it actually takes away the stack. So ESP moves up because we no longer need the stack. So it moves up and our box is gone because we popped it off, and that value is stored inside EAX because we popped the value from the stack and now we're storing it into EAX. So the way you can think of pop is it gets rid of the last thing on the stack, and since we set EAX, that's where that value is being stored into. I see a little bit of confusion. Is anyone still confused about the pop or push? Okay. Now we're going to be talking about the load effective address, which Evan will be taking over.
All right. So when we talk about the stack, when we were talking about the stack, we mentioned how we could store variables in it. So we could store things like we could store a number in it. We could store basically any value in it. So when we're doing something like move or add, when we do something like move, how do we know that how does the program know that we want to move the value at EBP, so the value we've stored in EBP versus the actual address? Because like we mentioned, EBP and ESP are both numbers that point to the address in memory. So how do we know that we want to reference the value at that address and not the actual address itself? And so what we have for that is we have the load effective address instruction. So what that is doing is say, I don't know, this wouldn't be a real address, but say you're looking at a stack and the address of EBP is something like 50. By doing load effective address, we're saying don't move 50 minus 4, don't move 46 into EAX. Move the value at EBP minus 4. So if the value at EBP minus 4 is 48 C6 FF, what? Move the address. Oh, you do move the address. My bad. So you copy the address from EAX from EBP into EAX. Then there's also an argument called compare. And this is used a lot if you have things like if statements and else statements. So what compare does is it takes two arguments and then, sorry, we lied, there's more registers. So there's this other register called the eFlags register. And what eFlags does is it's this super long register, but basically you can set different flags to 1 or 0, and that basically communicates information to you about what the program is doing. So for example, say you have, say you're comparing EAX, which is 1 to 3. What this is really doing, comparing EAX 1 to 3, is what it's really doing is it's subtracting it's subtracting 3 from EAX. So we take the value of 1, we subtract 3 from it, and then when you compare EAX to 3, we're taking 1, we're subtracting 3 from it, and then we just set all of our E flags in this register. So we have a sign flag, which is if this value is negative or not. We have a 0 flag, which is set if the result is 0. So one thing we can do is say we compare, say instead of moving 1 into EAX, we moved 3 into EAX. We compare EAX to 3. They're the same. So what we basically do is 3 minus 3, we get 0. So if we do a compare, and then we check our 0 flag, and we realize our 0 flag is set to 1, it's true, then we know the two values are equal. And so we can do this kind of logic similarly with our sign flag as well. If we see that our sign flag is set to 1, as in the case here, we know that EAX must be less than whatever we're comparing to, because we're subtracting 3 from EAX. And then also, if we see our 0 flag is not set and our sign flag is not set, what we can do then is go, okay, so it's not negative, it's not 0, so then we know EAX must be bigger than whatever we subtracted it from. And so you might be saying, oh, what is that? How does that really help us as an instruction? Well, what that does is it allows us to do things like for loops and allows us to get to the next instruction, which is jump. But before we get into jump, how does the computer actually know, what instruction, if I was the computer, what instruction do I have to process? And how it does that is through basically addressing. So every instruction on the stack is given an address. And again, we talked about those 3 special case registers, EVP, ESP. The final one was EIP. And what EIP is it's the instruction register. So it points to the current instruction we're at. So if EIP is at this value, we run push. If EIP is at this value, we run move. And then as we keep going down, as we increase EIP, it does a different instruction. And so since EIP is keeping track of all our instructions, exactly, so this is the example, so EIP points there, we push, we move, we push again. And again, what we were talking about is that little endian data structure. I know there was some, or that little endian notation. I know some people are having trouble with that. Basically, to us humans, this value is 80, 49, 15, and then 9. But when we want to represent it in, or there should be 0. So 08, 04, 9159. And that's how we would say this number out loud. But when we represent it in the computer, it's in little endian. So it's basically reversed. And we keep the bytes. So instead of that, we go 59, 91, 04, and then 08, and that's how we represent it in little endian. And so that's how we actually use the jump instruction. So what we can do is we can have our jump instruction, and we can say jump to any of those addresses we were just talking about. So if we go back, if we want to do a for loop, say we keep going down to the instructions, and then we get an instruction saying like jump 8049157. And then that means we would jump back all the way up to our move EBP ESP instruction. So using jump and giving it some address that our program has, that's our way to kind of create control flow and figure out you know, what our program's actually going to run. So for example, what JZ does is JZ is jump 0. So what it checks, we had that big E flag register. It checks, hey, is my 0 flag set? And if the 0 flag set, you know, jump 0, then it goes to the value there. And if 0 is not set, it just keeps falling through to the next instruction. It just ignores that. Example, 0 flag is set, and it goes to that instruction. And there's also certain variations on that we can get into. Basically, there's certain things you can do where I can, in assembly, I can label my different parts of my program with different kind of labels. So I could write a program where I say like, I give it a label like, I give it some label like L1 or label 1, and then I write a bunch of assembly code. And then I go label 2, and I write a bunch of assembly code. And what my program will do is it will, you know, it'll run down all the steps. It won't stop at any of these labels. But if I say, hey, jump to this label, then it will go back up and jump. So that's an easier way if I'm actually writing assembly for something. Those labels are an easy way for me to keep track of where I need to jump to. And then there's also the, you know, you could create functions and you could call those functions. So what that does is, or what the call function does, or what the call instruction does, is it allows you to call a function. And if we just jumped to the location of a function, we run that function, but then like what do? We run our function, and then it would just, how assembly would work is it would just keep following the next and next and next instruction. So if we ran a function, but we wanted to return to our previous code, we wouldn't be able to do that if the code for the function was lower down than the code from the actual calling function was. So what we need to do is we push EIP. By pushing EIP, it's our way of storing that address. Like, hey, here's where we want to return to. Here's the function. Here's the function we want to return to. So then we can run our function, and when it returns, we can pop EIP and go back to that same instruction. So we pop EIP. That's the address of the main. And so we just gave you like, I don't know, 8 different instructions. That's tough. No one's gonna remember all of that. So there's all these things you can find online where it's just, there's manuals and cheat sheets. And so if you want, you can take a photo of this. This is just some of the most used instructions. And so this will get you like a basic of like how to do assembly and stuff. And so we gave you all those instructions. It would be nice to take a photo of that. So what we want to do next is we want to do some a little bit of reverse engineering. So all you guys turn and talk, and the .L2, that's some of the labels we just talked about. So turn and talk, and kind of reverse engineer. You can ignore those first 2 instructions, but what is this program actually doing? What is this piece of code doing? Can any of you guys figure out? We'll give you about 5 minutes, and then we'll do a little walk around during that time and try to help you guys. Oh yeah, oh sorry, J and E is jump not equal. So when we do compare, if we do compare and the 0 flag is set to 0, so the 0 flag is not set to true, then it'll jump. And I'll walk around and help some.
How are you guys doing with the assembly?
Pretty dramatic, but alright. I don't love the instructions, and I don't super understand the stacks, but I think I have enough knowledge to figure trying to get out, so I test it through.
You can always come to the room to ask us questions, and also like in Too Dirty, you'll be spending like a good chunk of the semester on this. Like, don't worry, we're giving you more like a high level understanding of this. If you're interested, like you should look more into it, but like don't be too overwhelmed by the knowledge. We did like take a good chunk of that class and kind of like make it into a lecture. So
I think I'm taking 230 next year.
I see, but it's really mainly about this. So if you kind of like already understand this, like going into it, you'll be like.
So technically, yes, it's Q3. We tell them.
So when you go think about
It will run label 2 on
the
us,
example.
and label 1 we haven't
Have you
read.
complete so far? I think it's
But yes, you are right. We didn't really heard a question. Talk about any part of it.
So those first two functions, or so those first two instructions,
You can ignore the first two.
you can kind of ignore. Those are just a way for it to keep track of where to return to out that program. And so I would start that second move function, and just know that EDI is where EDI is where we pass it, or where we pass our like function.
That's you are using a different.
Removing some function argument to argument minus 4. Let's move that argument to EAX. Right, and then we're doing stuff to it.
We're taking a CDI value and we're putting that into that, we're putting that as a value for
Oh, so
an
all
application.
the arguments are, so the argument in this case is stored in EDI. So EDI is just this, this generic address on the stack, just to store it, argument minus 4. Then we move that into EAX, and then we start performing operations. So it's just moving argument 1 onto EAX.
Oh, that's just an AND operation, so that's just an AND operation, right?
Bitwise operation for
Yeah.
Sorry, this is what
It's
we're
the,
doing our
I'm trying to find a way to explain this.
There are several different.
Okay, so EX,
I don't.
So, this
so
one.
what I'm, okay, I
is,
think, I'll explain the bitwise, it's like a door, right?
The ant?
Sorry about that.
So, this is what it's doing, and it's storing down values.
We're using,
to it.
we're using Intel.
What if, so, this is
It's usually.
one and four,
Like,
maybe 0.
yeah, sure, you can report, just write it on Python.
And then, so let's say EX is set for value 4, right? And we're doing the AND operation on 1. So I'm gonna convert this to binary, yes.
But
EAX is
you could probably
Oh,
use
this is
that.
an example.
cheat sheet.
It's not such for,
This
this is an example.
reversible.
Yeah, but how can that entire thing be set up for?
Oh no, like the value stored inside. So like this will be pointing to a memory address. So let's say inside that memory address, because I believe we're using the D-word pointer, we're going inside this box, this address, and we're getting 4. Sorry.
Are you able to
So
just-
we're getting the value stored at the
I'll just
location
send
that
the
EX is pointing to. So we're getting the
like
inside,
cheat sheet
and we're comparing against 1, right? So the way we compare this is, I'm going to write this in binary, so this is 0, 0, 1, and then that's 0, 1, 0, 0. So if we do the AND operation, it's 0 and 1
And 5 minutes.
same. No, right? 0. Are they the same? Yes. 0, 1. So that would be our value that's now put into the EX. So this is 1,
Yeah, we'll come back to this.
or 8. So it'll be 10. So the value 10 is going to be stored at this location. So if it's more anymore, it's going to be 10.
So then we'll check if the old value and the new value are the same.
Test.
So we'll like come back to this example at the end if you like want to still keep working on it.
Okay.
The test instruction, I'm forgetting, but I think it checks if they're the same.
No, they do. They do. I think. They just check if they're same.
What does this mean? What does it mean again?
So we're running out of time, so we're probably going to.
Oh, wait, what was that?
Sorry,
Oh.
when does meeting, I'm just wondering, cause I have the volleyball game, but I can,
Oh,
I can cut
in,
into
like,
it.
okay, it'll be like 10 more minutes if you wanna stay, but you can leave. We're just gonna go over like an example. of-
If you also have Discord, you can ask questions on the Discord tonight or tomorrow. We can get
Yeah,
that.
we'll respond, so don't worry. Or you could also stop by our like club room if anytime we're there to ask any questions.
What room number?
It's in the
LGRT
tower.
202.
Yes, it's in the tower, the other building, the really scary one, the one with little architecture.
202?
212.
So
Say
if you
212.
go straight from the elevator, you'll see if it's open, then yeah, come in. Otherwise, it's closed. Feel free. So guys, we're running out of time, so we're probably going to come back to this example towards the end. But
Yeah, okay, now I'm gonna do a more simpler example. This had some instructions that you weren't familiar with, but you can look it up on one of the cheat sheets or the actual Intel x86 manual. So let's go through this example. This example doesn't have any instructions that interact with the stack. We're just going to be interacting with the registers and the flags register as well. So these are the labels that Evan was talking about, and we can know what parts of the assembly we can jump around to based on the labels. So let's start with the first instruction. EIP is going to be pointing to the address of the global underscore start, so that means we're going to go over here. And we're going to track the the values in the registers as we step through the program. So when you're working through assembly, you want to make a mental model of how the values in the registers and the stack change as you step through the instructions. So if we go to the move ECX3 register, or move ECX3 instruction, we're going to load the value of 3 and ECX. So that makes sense to everyone, right? Okay, cool. So next, we're gonna XOR EAX and EAX. What that means is it's just going to zero out whatever is in EAX. When you XOR something with itself, it just makes the entire thing 0. So we're just making the entire thing 0. Next, we're going to go to the add EAX and ECX. So it took whatever was in ECX, which was 3, and then added that to 0. So now we have 3 in EAX. And next, we're going to decrement ECX. That does just decrement by 1, like the DEC instruction. So now we're at 2. And now we have the J and Z, which is a jump if it's not 0. Or sorry, if it's not set to 0. So we have 0 in the 0 flag right now because when it looked at ECX, it's not 0, it's still 2. So therefore the flag is still 0 as it's not set. If it's set, it's 1. So if ECX was holding the value of 0, then ZF would become 1. But it's not set because it's 2, right? So it's going to see that, and then it's going to go back to the start of the loop. Did that make sense to everyone? I don't know if I explained that good. Okay, cool. So now we're back at the start, and we're going to go through the instructions again. So add EAX to ECX. So, and then decrement by 1. So what kind of structure is this starting to look like? Like in programming languages, like you have if statements, and then you have like print, like yeah, what kind of structure do you think this is working with? Yeah, exactly. So this is how a for loop would like translate into assembly. And then let's keep going through it. It's still not 0, so we're gonna go back to the start, and then we're gonna do the add, and then decrement, and this time it should switch to 1. Did you guys notice that it went to 1? Yeah, what's up?
No, which, register check.
Sorry, what's up?
That's the number register check.
Oh, okay. So do you remember the eFlex register? So the eFlex register has 32 bits. Each bit is going to be a 1 or a 0. And if it's a 1, that means like the flag is on, right? And then if it's off, it's like a 0. So if ECX is going to be equal to 0, then the 0 flag, the 0 flag, or the bit in the flags register that corresponds will turn into 1. Yeah.
How does it check ECX instead of like EAX?
It's, so the jump instruction will check the flags register, not ECX. You mean here?
So if ECX is 0, is it deflect?
Yeah, so this will set it, like this instruction, like when you run DEC, the computer knows to go and set, like because you provide ECX as an argument to the just like something that's built into these instructions. In addition to doing like add or subtract or decrement, they also go and update those flag values.
So is the E flag only applied to ECF?
No, so like if I had like EDX, for example, and I had 4 in it, EDX would become 3, and then it would go and update the E flag. So the E flags is just going to hold like flags as it steps through each instruction. Did that make sense? So now that it's set to 1, which means it is 0, it's going to keep going down. And now we have moved moved EAX into whatever the variable sum is pointing to. So we can assume that's like the return value that we're returning from this function. And then this is just up to exit out of the function. So what C code do you think we just went through? Like we said that it was a for loop, right? But we were doing some stuff with like adding numbers. And we started from 3, and we did stuff to that 3. So what do you guys think we just like stepped through in terms of C code here? Like let's think about what we did, right? We had 3, and then we added, and then we got our final result was our final result was 6. So we did 3 plus 2 plus 1. So what, like, do you guys like see how that maps to C code? Like a for loop where we add the numbers? Yeah, okay. Yeah. So when you're reversing something, in Cyber, like in CTF competitions, there's an entire category called reverse engineering, where they'll give you a binary, and then you can do the assembly in that binary with tools like ObjectDOM, or there's like a ton of tools that can help you. There's like Ghidra, which is actually going to take the assembly and try to make the C code that it thinks it maps to. So like reverse engineering in CTF is where you're given a binary, and then based on the assembly and based on using these tools, you have to figure out what it's doing, and then figure out how to manipulate the binary, or like in a way that in which you get the flag. So you have to work from the assembly all the way backwards to the C code. Does that make sense to you guys? Do you have any questions? No? Okay. Cool. Thanks for coming to the talk. Feel free to stick around if you guys have like more specific questions.
Also, very quick chill. Just a reminder to everyone: Miniman CTF 2025 is going to be this Friday, 6 p.m. If you guys don't already have a team for it, feel free to like talk to people in this room, and then we'll also have like a way to form a team at the start of the competition. But we do definitely recommend, if you guys are at all like interested in the type of stuff we covered today, and also for the rest of the semester, feel free. We definitely encourage you guys to come to the competition. It's a great way to learn more in like a nice gamified way with a bunch of other activity and friends there.
We'll have reversing challenges.
Yes.
We'll have a real reverse engineer